Hey everybody, now we're starting class. It's only 1:18 and we haven't done anything, but now I'm recording it and I'll share the screen. Do you have any questions from the other day?
Yeah, I wanted to ask you, since you brought up the airplane example with force and velocity and stuff, it's relevant to when an airplane's both engines stop at the same time, the plane keeps gliding. So what would that be in
Okay,
respect to velocity? It's just
well,
interesting. So.
first of all, when we talk about an airplane, right, and we talked about the four forces, and this is actually a good segue into something that I just needed to pick up on, is if we look at the engine, the jet engine of an airplane, how does the jet engine work? Looks like a bullet again. Shoot this off a cliff. No, what it does is it creates thrust by propelling air behind it. A turbo engine, if you had an airplane that had a propeller, something like this, then the propeller would push air backwards. So this is Newton's third law, which is common. What is Newton's third law? What does it say? What does it say in there? What does it say?
Isn't it for every reaction there's an opposite and equal reaction?
For every action,
Every action.
there is an equal and opposite reaction. So the idea is really what it is Newton's third law is what we call the conservation of momentum. You remember the formula for momentum? I mean, the answer should be yes. Yes, Paul, we know what momentum is. We're just not going to say it out loud because I don't want it to come off as a smarty pants. What's momentum? Formula. Sam! Oh my gosh. We just talked about this the other day. Remember Ryan goes momentum? I'm like, well, not really momentum, but I understand why you said that. What's momentum?
Mass times velocity.
Mm-hmm.
So if I've got mass, the air, times the velocity of the air going out, that is the action, which means everything else gets pushed forward. That's the reaction. Oops, reaction, right? So when an airplane's flying, it's throwing it out back, and that's creating, when I had the airplane, right? Here's the airplane. I had that forward thing called thrust. Really what it is, I'm thrusting backwards to go forward. Okay, so let's be a geek for a second, because I want to know, I want to know why students are, what they think about. So I'm going to ask you a question here, because I've got one other fun thing for you to watch today. I always come up with fun videos. Have you ever thought about being on a spacewalk? Have you ever thought about what it's like to be on a spacewalk? Have you ever considered what would happen if the cord cut and you started floating through space? Okay, Shannon, you thought of that. So what would you do?
Well, I wouldn't know, so probably panic.
Well, panic might be, yeah. I mean, I might too.
Well, wouldn't it
What you'd have to
people
do,
say that you might float into space, but you might start to orbit or something? I'm not.
well, yeah, because remember, but see, what happens is as soon as you get untethered, when you're flying around, do you understand you are now moving inertially? You're moving inertially because whatever you're moving at is how you're moving. If the plane or the spaceship is away from you, then you need to go from this not moving toward the spaceship. So how would you do that? What would you do? What you would have to do is find a way to project away from the spaceship an object. Maybe, I don't know, take off your glove and throw it the other way. And then you're going to respond by going in the opposite direction. Right? I'd carry like a pistol around and shoot the gun. Don't know if the gun would go off. I'm not sure if would the gunpowder light without oxygen?
Why would it not work? Because there's no combustion.
That's what I'm thinking. I wonder if that's the case. Bummer. Well, then maybe an air gun, just with pressure. Shoot the ball, because when the ball goes out backwards, it's the mass times the velocity in one direction, and you will go with a much larger mass in the opposite direction. So you will go in an opposite direction. You won't go as fast as the ball. That would be bad. Shoot a ball and then smash into the parent and knock yourself out and die. You'd start fading back, but at least you'd move, because as long as you're accelerating, as long as you have the force, you accelerated for a second, it's called an impulse. And then you just kind of move toward the thing and you'd eventually catch up, unless they are flying away from you. Like, leave them behind, and then be like, in space. And then you'd have a movie and you'd be Sandra Bullock. Do you ever see that movie?
I
Gravity?
haven't seen it, but I know what you're referring
Just
to.
Gravity. George Clooney he drifts away. He did something like that. Anyway, so that's the action-reaction law. So Shannon, you're talking about, well, what happens now if the plane, the engine's cut out, right? So you have drag, which is still existing, right? This is still there. You still have weight, and you still have lift because it's moving. But then what happens is this goes away. So what's the net force? The net force is this, which means what will this airplane start to do? The plane would start to slow down because it's not going to go forward as fast because you have no thrust to balance the resistance. So you're going to start to slow down. Here's the thing. Do you know what causes lift? Zach, what do you think? Do you know what causes lift?
Is it like the wings catching the air?
What about the wings?
They have like the flaps in the back that you can like rotate up and down.
Well, yeah, but without the flap, because the flaps, you're not using the flap until you stop. What happens is you have air going up and over the wing, and you have some air coming up and under the wing. But the way the wings are designed, this area is larger, this area is smaller. So you have the same amount of air being moved over that. Remember, pressure is force over area. Remember that formula? So if the blue area is bigger, what's the pressure? The bigger the area, the smaller the pressure, right? You have the same amount of air going up and down, but you have a larger area. So the bigger the area in the blue. So that means there is a force this way, which is less than the force upward. The net force points which way?
Upwards.
The net force is upward. That is called the pressure gradient force. That there's a difference in pressure under the wing and on top of the wing. And that creates the upward force. And when the airplane's flying straight at the same speed, that amount of lift is equal to that amount of weight or gravity. Weight. Remember we said F equals ma? We're saying weight equals mg. Weight is a force. Gravity, and we'll deal with that today, is an acceleration. So this is the same thing. Weight is the force, gravity is the acceleration. So the amount of this upward force, which we call lift, by the way, this is called the Bernoulli effect, if anybody's interested. Zach, if you ever heard of that?
The Bernoulli effect?
The
No.
Bernoulli.
Bernoulli?
This force becomes bigger the faster the airplane's moving. So the faster it's moving, the greater the upward force. So what happens when the airplane slows down? The upward force is less. So this becomes less, and what does the airplane do? It starts to come down. But if the airplane goes down, okay, so now imagine the airplane starts moving down like this. And this is how we think about what we did the other day. The velocity of the airplane is now that direction. Which way is gravity? Gravity is down. Do you see that there is a component of the motion in the same direction as gravity? So what will that cause the airplane to do? Speed up going down. So as it goes down, it speeds up. And what does that speeding up do? It creates more flow over the wings, creates lift. So it doesn't go down like a rock. You're actually generating it to keep it up. Now, because there's no thrust, I'm going to slow down more and more. What I do is I use the airplane to dive to pick up speed. But I'm also getting closer to the ground. And at some point, I'm going to lose. Eventually, it'll come down. But that's what gliders do. Gliders can go and fly. And sometimes they use thermals and they get enough that they can lift and stay up there for a while. They eventually come down because resistance will eventually win because there's no more thrust. But it takes a while. And an airplane, even if it lost both wings at 30,000 feet, it's not coming straight down. It'll take a long time to get down. It takes 20 minutes to do that. And then you better believe the pilot's in there trying to start their engines up. And if they don't, what do? They go, I'm going to see if I can maneuver the airplane to land over there, and I'll just land it with no engines. It's daring. But you could. No, you know why they don't land jets with no engines? Well, that's stupid, first of all. But the reason is because if an airplane had that happen, where is it going to land? Where would you land the airplane? You may not be anywhere close to a runway. So where would you have to land an airplane? And people do this a lot when engines fail.
I know for like the prop jets, they say like streets if you really had to.
Yeah, I mean, the best way to do it is a highway. And
it was actually a situation here several years ago that a highway near here was actually used as a runway, so for an emergency landing.
Yep.
And actually the plane is still right there on that highway. It's on the side.
You know that the interstate highway system, from what I've been told, I don't know if this is true, but they always had 5-mile stretches of straight because they could use it as a runway, even the big jets, if they needed to. So highways, you have to look out for the other cars in the way. And you have to go, hey, I'm landing, and you don't have a horn on there. Can you imagine if a pilot had horns on there? And you'd be like, who's honking at me? You know, somebody lands on top of them. But they do that. This has happened many times. So do you remember who Sully is?
I've heard of
Captain Sully. He landed in the river. Amazing. What a hero that guy is. Anyway, so that's what's going on with those forces. Now, there's something I'm going to show you. Air Force jet engine Man caught. I think this will do it. Man sucked in. Let's try that. Is this it?
True story, yes, using Twitter to document a horrific accident as the airplane gets stuck into a plane engine. Flight Radar 24 reporting it happened on board an Air India flight.
Oh no, this is not.
It happened at Mumbai Airport, and TV reporting what happened.
Oh, here. Have you ever seen this one? Look how many views, 1.7 million views.
A routine inspection of a Roman A-6E intruder plane during the Persian Gulf War almost resulted in a fatal accident. This video shows the moment Petty Officer J.D. Bridges was sucked into an engine while checking the launch mechanism of the aircraft. The flight deck crew member was stuck inside the engine intake for 3 minutes, but managed to come out practically unscathed. But how did Officer Bridges survive? It was only thanks to a series of lucky strokes.
Did you see that? He got sucked into the airplane engine. You don't want to walk in front of a jet engine. That's a bad idea. That's why. He looked like I Dream of Jeannie. He just gets sucked in there like...
Stuck inside the engine intake for 3 minutes, but managed to come out practically unscathed. But how did Officer Bridges...
And he survived. He hit some frame in the back and he got stuck into it, so he didn't go through the blades. Because had he gone through the blades, he would have been, you know, smoothie. So that's what the action reaction law does. So rocket ships, action reaction law. They thrust down, rocket ships go up. Oh, you want to watch this? Rocket ship failures. I want to see old. I don't know.
Challenger.
No. Here, let's try this one. V2 was the one that was developed in Germany in World War II by Werner von Braun, who was then captured by the Americans and brought and started our program. That doesn't look like a really bad failure. Well, I guess that's a bad failure if it's coming straight down.
Oh my God.
That's not good. Ooh. That's kind of fun. So here's the thing, right? And this is something I thought I would tell you this. This is the difference between science and engineering. Science is easy. I need to generate enough thrust to overcome gravity, and then I accelerate upward, right? Engineering goes, yeah, but how do we do that? We throw a lot of stuff there, but we have to control this. And if we're not exactly right, it turns. And if it's a little bit too low, it falls back. I mean, there's so much technicality in designing it. That's where the real struggle is. From a physics standpoint, it's like, yeah, just I have to have enough thrust up to overcome gravity coming down. Well, how do you do that? And then there's all sorts of cool derivations. It's really fun. I mean, what a fun thing this must have been. Did you guys ever play with rockets as kids? What kind of rockets did you have? Tell me the type of rocket.
Well, we had to like do this thing in high school where we had to build a rocket, and then whoever's rocket got to the highest elevation point wins or something.
Oh, that's kind of cool. So what did you fuel it with? You remember?
I think there was like we had like put like whatever like it wasn't gunpowder, it was like something that would ignite into
Oh.
canisters, and then they would like make it go up or something. I'm not quite sure.
Oh, that's cool. Do you guys, anybody else?
I remember doing a lot of that when I was little.
Do you ever shoot bottle rockets?
Yeah, when I was in 8th grade, we had, for science, we had to do it with baking soda and vinegar. We had vinegar in the bottles, and then we had to put like a packet of baking soda in it, twist the cap on, put it upside down, and then like whoever's went the highest, like they won.
Oh, that's kind of fun.
Mine did not go very high, but
Did you guys ever have those little things with water that you would pump up there and then release it and it would shoot and spray water out backwards? All this is so that's all of Newton's third law. So it's kind of fun. That's truly, right? That's truly rocket science. So we got to know about gravity. We're going to talk a little bit about that in a second here. So any other questions about stuff? So let's review what we had the other day, right? What are the things that we need to keep in mind? Number one, we have the law of inertia. An object at rest or in motion stays that way until acted upon by a net external force. So my phone, is there a force acting on this? Yeah, gravity, it's weight, but there's also the table moving up. So the net force is 0. If I remove this force, then the net force is gravity. Gravity points down. Now, what are the two things that can happen when a force is applied? Actually, what's the one thing that happens when a net force is applied to an object?
There's some type of motion.
No, because it could be moving already. When a force is applied, what's the one thing that happens?
The object accelerates.
The answer is there's an acceleration. The object accelerates. Remember, listen to this closely. An object always accelerates in the direction of the net force. Got to keep that in mind. Always accelerates in the direction of the net force. If that force is pointing parallel to the motion, what changes?
Speed.
Speed. If it's pointing perpendicular, what changes?
Direction.
What if it's neither all parallel or all perpendicular? Then both things change. Okay, and the change of either speed or direction is a change in the velocity. A change in the velocity is an acceleration. The motion becomes accelerating and it takes a net force. Does that make sense? All right, so here's a fun one. I'm going to put Sam up on, Sam's going to be doing this one here. Okay, so what I have is, I have a cliff. So no guns on this one, Sam. I hope, maybe you're not into guns, and then so it's just there. So you're still going to be violent. So one day I'm over here. Oh, you know what? I need a larger head because I have to draw pictures. So here I am one day standing by a cliff. Now this is me, and this is clearly not me because I am aquaphobic. What is aquaphobia?
Fear of heights.
Fear of heights. I would not be anywhere near the cliff. I went to the Grand Canyon and I'm 20 feet from the edge because it's
Yeah.
not
Same here.
okay. Well, Sam comes over here, and Sam's angry because I make fun of him all the time. So I have to give you a larger head too because I have to draw your expression on there.
It's only fair.
And you're like, you're mad at me. Okay, and you're gonna push me off the cliff. Okay. Now, when he pushes me off the cliff, this is what happens. Oops, I disappeared. No, I'm over here. And I'm still smiling. Okay. So what we're going to do is we're going to initiate this as time starting. So time equals 0 seconds. What is my velocity initially?
Is it 0 as well?
0 meters per second, right? Because I'm not moving. What is my acceleration?
Is it just gravity?
Gravity. You know what the acceleration of gravity is?
9 or 10, I guess.
I'm going to say this, okay? I know physics teachers, because they're all cut of the same cloth, and they're all anal, like, it's 9.81, and they get really all pissed off at this. You ever had that in high school? Right, 9.81, you can say 10. And I say this, what's 5 times 9.8? Go. What's 5 times 10?
50.
Okay, that's why I do 10. If you start designing rockets, then we can use a different number. Anybody going to design a rocket for NASA anytime in the next 3 years? Okay. So we're going to use 10 meters. Now look at what it says. Remember, this is meters per second squared. So a meter per second squared, which is what this is, right? Meters times, remember we did this with notation, is the same thing as meters per second times per second. But please excuse my dear Aunt Sally, I can multiply anytime I want. So what this really is this is meters per second per second. And this is really important. I want you to think this way. Okay, Lena, I want you to think this way. When you see this, it's meters per second squared. That's what the unit of gravity of acceleration is. But I want you to think it's a meter per second per second. It's a meter per second per second. That'll be important coming up. So is that what my acceleration is here? Is that what you're saying, Ryan?
Yeah.
Anybody disagree? Julia, what do you think it is?
I mean, that makes sense because everything else is 0, so you would just have
Well,
gravity.
why wouldn't my acceleration be 0? Anybody think that's 0? Nina, did you think that? How do we know it's not 0? A lot of people do this. They fight me on this all the time. It's 0 acceleration. What is an acceleration saying? An acceleration is dv dt, right? It's the change in the velocity in a given amount of time. You might have said delta v over delta t. That makes sense? So if the velocity changes by, I don't know, 10 meters per second, or no, let's go 3 meters per second. Do you understand that's 3 meters per second is the change in the velocity in 1 second, meters per second per second. So I'm talking about a change in the velocity in a given amount of time. Why isn't it 0? Because if it were 0, that means if my acceleration is 0, Newton's second law, if this is 0, what does that make the force? Do you agree that there's a force acting on me? And what is that force?
Gravity.
Right? Well, technically it's my weight, mass times gravity, but it's gravity, okay? It's pulling me down, which means an object at rest. Do you agree that I am at rest to start? But am I going to stay at rest? The answer is yes. I am going to stay at rest for a little while. Why? Is this really me? Is that a picture of me? This is a cartoon, isn't it? And cartoons, if you watch cartoons, they don't fall just because they're hanging off of a cliff. When do cartoons fall? What do they have to do first?
Don't they
Good.
run in midair?
Well, not first. They do run in midair for a while.
They always look down.
They have to look down because if they're oblivious, they're not falling. They look down to see that they're going to fall. Then what do? Then they look up at the camera. And then what do?
Smile.
Most of them pull out a sign like yikes or something. Help. Don't they usually carry a sign? And then what do?
They fall.
Now they fall. But how do they fall?
They only fall and the sign doesn't.
That's possible, right? That's possible. How do they fall though, individually? Their feet go first. Their body gets really stretched out. Their head stays there, and then their head snaps back. So they actually stretch and then fall like that. And then if it's a sign or the top of a mountain or an anvil or a piano, they'll fall faster than the piano, and then the piano will fall on top of them afterward. There's actually, if you want to take a look at this on the internet, it's called O'Connell's Laws of Cartoon Motion. It's kind of funny. But that's how cartoons fall. But that is not how this is going to fall. This is going to fall that I'm going to be moving when? When do I move?
Instantly.
What'd you say?
Like instantly? Like do you just
Okay, so Zach's using a word and says instantly. What is speed? I'm gonna go on a little tangent here. What is speed? What's the definition of speed? Or velocity? Isn't it the change in the location over time? So imagine this. Imagine that I say to you, I have a car driving at 60 miles an hour. What does that mean? It means that in 1 hour, I'm going to have driven how far?
60 miles.
Does that mean I'm traveling at 60 miles an hour? See, you guys, this is really important. I want you to think like a physicist. This is really, or a mathematician maybe. This is really important. If you travel, so I go, here's an assignment. You drive, you're 60 miles away 1 hour later. Are you traveling at 60 miles an hour?
you could be, but you could be like speeding and then slow down towards the end.
So what have I done? If I travel 60 miles in 1 hour. What does that mean, Shannon? What do you think?
You stayed at a constant speed.
I didn't say that I did. Could I have gone faster and slower and still made 60 miles an hour? I mean, you know this, like you have to be someplace in 1 hour, 60 miles away, and you have a stoplight. What do? Are you going to make it in time? What do you do to compensate?
Speed up.
Don't you go faster to compensate? So you're like, oh, I'll go faster. Because if you go 60 miles in 1 hour, what have you really determined? Not your speed, but your what?
Your average speed?
That is what we would call your average speed. So in here, folks, what has happened is that this is not really the velocity. This is what we call the average velocity. And 60 miles in 1 hour, do you agree that's 60 miles in 60 minutes? That's the same thing, right? So what if I travel 1 mile in 1 minute? What's my average speed?
Still 60 miles per hour.
60 miles an hour. What if I go 1/10 of a mile in 1/10 of a minute?
60 miles per hour.
What if I go that much miles in that many minutes?
Same 60 miles per hour.
So do you understand the average has all been 60 miles an hour? Now imagine that I have a car driving by me, okay, and I have the world's fastest camera. Do you guys know anything about how cameras work? The camera opens the lens and then closes it, lets light in. And it opens it for a time period, maybe a 60th of a second. So if something's moving fast, what will happen to the object?
It'll be blurred.
It'll be blurry. So imagine I have the world's fastest camera. It's open like instantaneously small so that the car doesn't get blurred. And then I show you a picture of that car. And I'm asking you the following question. How fast is the car going in that picture?
Probably say it's at rest.
Okay, Zach says, he doesn't just say it's at rest. He goes, obviously it's at rest, as though he's a like common knowledge would say he's at rest. Do you agree with him? Lena's like, yeah, of course I agree with him. So you're telling me a car that's going at 60 miles an hour, when I take the picture, the car slams on its brakes, comes to a complete stop, poses, smiles for the picture, and then in 0 time goes 60 miles an hour again. That's one hell of a car. I'm asking you how the car is driving at 60. Why would you think that it's going to stop and then go again like that quickly? Isn't the car driving at 60? In fact, I could prove that to you, because what would I take a picture of to prove to you the car is going 60 miles an hour in the picture?
Wait, are you in a car too?
Maybe.
So your speedometer?
Couldn't I take a picture of the speedometer? Does the speedometer go to 0? Does it say 0 when I'm going at 60? The speedometer is telling me the instantaneous velocity, the velocity now. So look, with this whole thing, we said 0.001. How about if I went 0.000 infinity 1 miles? How far have I gone? Basically, nothing. This is basically 0. What's the denominator going to be? How many minutes? If this is basically 0, because in the picture, isn't the car going at 0 miles? It's not moving. How much time did it take? 0 seconds. But the car is still 60 miles an hour. Because this would be, so you're saying, what I'm saying is this. Let me do this. Let me just erase this so it's not so messy. What I'm saying is this, guys. I'm saying the car is going 0 miles in 0 minutes. But I kept doing it by dividing by 10. And so what's the speed? We know that the speed is no longer an average. It's 60 miles an hour, instantaneous, which is the way I write this. I go with the velocity. When I put average, when I mean average, I mean average. When I mean instantaneous velocity, I mean that. But you know what you say when this is 0 over 0? Do you know what you call the formula? See, in here, how long is this? When I was using this formula, that was some amount of time. I have a stopwatch. I start at a point in time and I end at a different point in time. Are those the same points? No, they're different points. Delta X or delta T. And in that delta T time, which is a duration, that's what that word means, you have gone a distance. But is this a duration? This is an instant in time, a point in time, now. Not between now and then, now. How far do I go? 0. I'm at a point. But there still is a velocity, which we call the instantaneous velocity. So this requires how many points of time?
At least 2.
How many does this require?
1.
This requires 2 points of location. How many does this require? 1. A point in time, that's its instantaneous velocity. It still has meaning. So remember how I said early on, I said, for you, this is the same thing as this. You could use either. Now you can't. Now you have to say, this is between 2 points. This is at 1 point. But here's the thing. What do 2 points define?
A line.
Do you agree 2 points define a line? Are you following me, Isaac? Does this make sense to you? 2 points define a line. Isaac, can you define a specific, unique line at 1 point?
Sorry.
Here. Look at this. I have a point and I have a point. Do you understand there's only one line that goes through those 2 points?
Mm-hmm.
If I change the line, does that line go through both points?
No.
So do you understand how many lines go through those 2 points?
Well, there's one line.
Just one. That's what we say, a unique line, 1. Okay. And how many points did I need to find that unique line?
2.
Right. Can I define a unique line with only 1 point? In other words, can I define a unique line at this point only?
No.
How many lines could go through that point?
An infinite amount could.
Correct. Unless I put that point on a circle. Is there a unique line that goes through that point if that point were on a circle?
Yes.
What is that called?
A tangent.
If I change the slope of this line, I intersect the circle at 2 points. This is a unique line at a point if that point is on a curve. No, that's what we did the other day, right? We were talking about this the other day, right? We said the velocity is any point on that, its tangent. Because if I cut the string, do you agree that that rock would go off on a tangent in a straight line? That's what that means. So this, we're going to find out, and I'll show you using examples, that this is defining the slope of a tangent. You'll understand what this means coming up. But that's what I'm defining with this.
That's a question.
That's a question. That's what I'm going to do. I can define a unique line at a single point. That's what that does. And the unique velocity at a point in time is the instantaneous velocity. So do you understand that I could ask the question, when am I at rest? When is my velocity 0 meters per second? Now you have to give me an answer to that question. When is, so how will you, I tell you what, write down the answer. Force yourself to write the answer. Based on what you see on the screen, when is my velocity 0? When am I at rest? And you write down a physical answer.
Are you saying when velocity is 0 on the circle there?
No, hold on. What I'm saying is this. I get rid of all this stuff, okay? In this thing here. When is my velocity 0? So you're answering when. What did you write down, Julia?
I put when both the change in location and the time are both 0.
Okay, I know why you're thinking that, but that's not the way you would talk in real life. So if I were to say to you, when does this class begin? How would you answer that?
1 o'clock.
At 1 o'clock. Do you understand? You've used the word at, first of all. And what have you given me? Haven't you given me a single point in time?
Yes.
Right? When does this class end? At 3:25. If it's 3:26, is that the correct ending time? No, you could say, well, you're running long, right? And that's when it ends. That's fine. But when's it supposed to? At 3:25. So that's the way that you need to answer this question. When is the velocity 0 meters per second? Ryan?
When time is 0?
Or, well, you could say when time is 0, but you'd say at 0 seconds. At 0 seconds, that's when the velocity is 0. And at 0 seconds is really when it starts. Now, what happens a little bit after this? Will my velocity stay at 0? No, because I am accelerating, which is saying that my velocity is changing. So at 1 second, the velocity is different. At 0.1 seconds, the velocity is different. At 0.001 seconds, the velocity is different. Instantly at 0 is when I'm not moving. But instantly after that, if I go a little bit further into time, my velocity is no longer 0. Why? Because I'm accelerating. So then the question is, all right, I start to fall. Oh, didn't mean to turn pink. Oh, I need a bigger head. Because now I'm a little bit, oh no. And Sam spun me a little bit. So now the time is 1 second later. It's at 1 second. What's my acceleration?
Ten meters per second.
10 meters per second. Because what force is acting on me?
Gravity.
Gravity. Do you understand that it's the same as it was before? There's the only force acting on me. Now there's air resistance. Let's neglect that. Is gravity. It's the same as it was before. Gravity is still giving me an acceleration of 10 meters per second. What is my velocity at 1 second? Isaac, what do you say? How fast am I going now?
10 meters per second.
Okay, Isaac says 10 meters per second. Do you agree or disagree with that?
I agree.
Okay, Zach agrees with you. Although Zach was wrong on the other one that everybody agreed with. So. What do you think? Do you agree with them this time? Lena, what do you say?
I'll say yes.
Shannon? Ryan?
I'm not sure.
All right, Zach, how did you get 10?
If you're like moving, so if your acceleration's 10 meters per second, and the change in time has been 1 second, then you would have only moved 10 meters per second.
You would have done what? You would have done what in only 1 second? That's what you said, right? What would you have done in 1 second?
You would have changed your position.
No.
Move downwards 10 meters.
No. Look, you said accelerate. You know what the acceleration is. Do you agree? You know that. You know that equals that, doesn't it? If the acceleration is equal to the change in the velocity over time, do you agree that the change in the velocity is equal to the acceleration times the change in time? Does that make sense to you guys? So how big is A?
A is 10 meters per second.
How big is delta T?
1.
1 second, it's the duration. So that means what is 10 meters per second squared times 1 second is 10 meters per second. What is 10 meters per second?
Velocity is 10 meters per second.
No.
Oh, the change in velocity is 10
The
meters per second.
change in the velocity is 10 meters per second. Using this you've told me what the change in the velocity is, which is how much? 10 meters per second. What did you start with?
0 meters per second.
0 changed by 10 is 10. This is actually the velocity at 1 second is really equal to the velocity at 0 seconds plus the change in the velocity. Does that make sense to you guys? So in other words, why is this 10? Because 10 equals 0 plus 10. This acceleration of gravity and the time allows me to calculate the change in the velocity. That's why I said acceleration is 10 meters per second, because my velocity will change by 10 meters per second for every second I fall. So what would my velocity be at 2 seconds? No, I'm just giving up. I'm smiling again.
20 meters per second.
My velocity is 20 meters per second. See, this is my instantaneous velocity. It's my velocity at 2 seconds, because from the beginning to here, I have changed by 10 meters per second, and I've changed for 2 seconds. So I changed by 10, I changed by 20. So that 20 is 0 plus 20. My acceleration is always 10 meters per second squared. So if I were going all the way down, big cliff. At 8 seconds, what's my acceleration?
Is it?
It's the same, 10 meters per second per second.
Because it's a result of gravity alone. What's my velocity?
80 meters per second.
Because in 8 seconds, so look, watch this. In the duration from here to here, delta t is 8, right? 8 seconds. The change in the velocity would be what? What's my change in velocity?
80 meters per second.
Right? And why is my velocity at 80 meters per second? Because what did I start with?
0 meters per second.
So the rule is my final velocity is always what I start with, the initial, plus the change in the velocity. So I got to know what this is. And then I add the change, which is 80 meters per second, to 0 meters per second. And I finally get to 80 meters per second. So here's the thing, right? What if Sam had thrown me down so that my initial velocity were 2 meters per second downward? So he threw me down and let go of me. What would my velocity be at 1 second?
20 meters per second.
How many?
I mean 12 meters per second. Not
12 meters per second. Because what would I have changed my velocity by? 10 meters per second. I started at 2, I changed it by 10. This would have become 12. What would this one have been? What would it be at 8 seconds?
Would be 82 meters per second.
Be 82. Because for 8 seconds, I would have changed my velocity by 80 meters per second. I started at 2, I ended at 82. Do you see how this works? Now, that's the easy part. Now, the next question is, during that one second, how far do I fall? Get rid of all this stuff. That's good. I love this. I love being able to use this pen. I like that I can just touch a line and it goes away. So how far do I fall in that 1 second?
10 meters.
Okay, Isaac says 10 meters. I want you guys as a class, hold on. I want you guys as a class
But if you're falling, I think you're gonna go at a constant acceleration while you're falling. There's not gonna be much change in the speed of how you're falling.
Well,
Now listen to what Isaac just said. Respond to that.
Well, I agree with that because I feel like with a car though, that has a lot to do with like, I wouldn't call it human error, but your speed could be fluctuating. But when you're free falling, that's just gravity and your weight, so that doesn't change.
What doesn't change? You said that doesn't change.
The acceleration wouldn't change.
What is an acceleration? You see, what happens when you guys speak out loud is all of a sudden you have past thoughts in your head. And a lot of those thoughts are wrong. But you start to verbalize them, and then I'm like, whoops. So do you know how people always say, do you know what gravity's acceleration is in feet per second squared? It's 32 feet per second squared. I don't know. If you ever heard somebody say, oh yeah, well, something's falling and then it falls at 32 feet per second squared. It falls. What do you think falling means to you in your brain? What does the word "it's falling" tell you? You're watching an object and you go, it's falling. It's falling at what? If I said it's falling at, what do you think that means?
The rate of gravity.
Not the rate. If I said how fast are you driving? I'm driving at 30 miles an hour. Don't you use words like at to talk about the speed? So you're falling at some speed is what you think. Isaac, you said that, right? And you said, well, it makes sense with the car, but not with things because you said the velocity doesn't change. But look what I'm showing you here. What's the velocity doing?
Changing.
Oh, well, then why did you say the velocity doesn't change when you're showing me clearly the velocity is changing? Do you see what I'm saying? So, Ryan, say what you said again. Re-explain it to convince them that you're right. Be assertive.
So like the acceleration is going to be constant, but acceleration is the change in the velocity. So as the velocity is going up, it's going to be going you're going to be falling at a faster pace at 1 second than you are at, say, like 0.5 seconds.
And
Yeah,
what does going faster mean?
You're falling more meters in the same amount of time.
Remember a long time ago, we did Math Lab 1 and we talked about what's going faster, how to do it. And I love the way Ryan just said that. You're falling fast, you're falling further in the same amount of time. And I like the way that you said in a car, if you speed up to go to 10 miles an hour, you won't go 10 miles in 1 hour because you were slower than that. And I even asked you earlier, I said, when you're driving a car, if you stop at a light and you're just driving at 60 miles an hour, will you make 60 miles in 1 hour? What would you have to do? You'd have to go faster than 60 miles an hour to make up. So this is just miles an hour. We're using meters per second, same thing, distance over time. So we're saying, will I go 10 meters? When could I go 10 meters in 1 second? And Isaac, this is kind of what you were thinking through, but you were backwards on it. When can I go 10 meters in 1 second? Would you agree if I were traveling at 10 meters per second the whole time? Am I traveling at 10 meters per second the whole time? When am I? So answer this question. When am I traveling at 10 meters per second?
in the first second.
No. Not in the first second. When am I traveling at 10 meters per second?
Is it at 1 second?
At 1 second. What am I doing right before 1 second?
Speeding up to 10 meters per
Well,
second.
yeah, I mean, yes. But what's my velocity just before 1 second?
9.999 meters
Okay,
per second.
right, less than 10. I think that's the easiest way. What's happening right after 1 second?
You're right above 10.
A little bit above 10. So when am I traveling at 10 meters per second exactly? At 1 second. Before then, I'm going slower. If I'm going slower that entire second, and I'm only getting to 10 at 1 second, could I possibly go 10 meters in 1 second? I love to watch. Isaac, I love what you're doing right now. This is, can I be honest with you guys for a second? This is when I see students, this is what they don't do. Students in classes, I'm telling you this when you go to classes, they're not doing what Isaac just did right there. Anybody see what Isaac did? He was thinking. Do you know how I know he was thinking? Because he was trying to figure something out. And when they're thinking, their eyes go in a different direction. You have to. So if you're actually trying to process something, your eyes go into a corner. I don't know which way. Up. So I saw Isaac doing this. He was thinking. Most students don't think in class. They scribble, write stuff down. And if they're writing stuff down, they're not thinking. And if they're not thinking, they're not figuring stuff out. So, Isaac, good job. Can you answer my question? I don't even know what the question is. I totally forgot it.
Yeah.
If I was only traveling at 10 meters per second at 1 second, and before then I was going slower, could I possibly make all 10 meters in 1 second? Now, Zach, I heard you when we started, when I was first going down the stairs, I heard you explain something. You want to tell me what you said?
I said we would use the velocity equation.
Okay, we would use the velocity equation. We use the velocity formula. Okay, so we're going to use the velocity formula here. Which one did you use?
I used well, they're both the same, right?
Are they both the same?
Well, I think when it comes to like using numbers, it wouldn't change.
What is this equation telling me?
The average,
What is this one telling me?
the instant.
Instantaneous.
Use
So
velocity
if,
instant.
if I want to, so what you said to me, my friend, is you said, if I use this, so let's take a look at this. V average equals the distance, delta x is a distance over a duration of time, 1 second, correct? And we know that we should write down what we know, but delta t is equal to 1 second. That's the duration during this 1 second, in this 1 second. Those are the words that we use to describe them. Okay, and I'm trying to solve for what? What am I trying to figure out? Delta x, which is the distance. How far did I fall, right? That's a distance. So the formula would be that delta x equals V average times the time. Then the question is, if I want to know this, what do I need to know? This and this. Do I know this? Yeah, 1 second. What's this?
Oh, I see. Then that would be that would be using like 5 meters per second instead of a 10 meters per second. Because you'll find the average between the two.
You have to know the average, but do you understand the average is always changing? So why did you say 5 meters per second?
Because you add the two averages up and divide by 2.
Did you hear what he said? You add the two velocities up and divide by 2? You're taking this and that and dividing by 2? Is that right? Okay, I want you to remember this diagram because I'm going to erase it now. Actually, no, I'm not. I'm going to keep the diagram. I'm just going to erase things I don't need to worry about for a little while. Before I erase this, do you understand? I'm trying to figure out delta x. What do I need for the distance? I need the average velocity times the time. I average 10 meters per second or 18 meters per second or 60 miles an hour in some amount of time. Then I can tell you how far I go. That's what I'm trying to find. So, long time ago, you want to hear a cool little story? There's some of the famous mathematicians. The funny thing is, I was listening to a podcast last week about mathematicians. Can I just tell you, COVID has made me a flippin' geek. All I do is listen to information. I walk every day. Do you guys have a little Fitbit or an Apple Watch that tells you how many steps you take? Does anybody use that, or any parent use that? I'm old, so I think about this. I walked 15,000 steps a day. I have walked 15,000 steps a day for 210 straight days. Do you know how long it takes to do? That's like 15,000 steps is around 6 2/3 miles. And I'm on computer. So this is a lot of walking. When I walk, I listen. I listen to stuff all the time. I'm a geek. And I was listening to somebody talk about my favorite mathematician is, and really, God, I am so weird. Such a nerd. But one of the guys' names was Green. And when Green was a little kid, he was this brilliant, brilliant mathematician. And he thought different. And most mathematicians are weird and they think weird. So he was given a test or an assignment by his teacher. The story is like 2nd grade, maybe 5th grade, I don't know. And the teacher says, I want you to add up the numbers from 1 to 100. That was like busy work, because teachers like, I'm just going to give my kids busy work. They'll shut up for a few minutes and I can do something else. So if I said to you, I want you to add up the numbers from 1 to 100, what would you start doing? Anybody know the answer?
So like 550.
Well, here's what the kid wrote the answer down. Everybody else is 1 plus 2 equals 3. 3 plus 3 equals 6. 6 plus 4. They would write it down little by little. That's what they were doing. They were practicing addition. And he just goes, and he wrote down the answer. And the answer is, oops. And the teacher goes, how did you know that? And he goes, well, I just saw it. Because he's a genius, right? So what he saw was this. He saw the numbers lined up. Make sense? Because that's what you're adding. And then he says, well, wait a second. What if I put the numbers next to it backwards? Right? And then he says, what if I added up all the numbers in the column? What's the first column? 101, 101, 101, 101, 101. How many columns does he have? 100. 101 times 100 is 10,100. But he says, but I have twice as many numbers. So you divide by 2, and you get 5,050. Kind of cool, right? I mean, that's a pretty smart kid, that he can see that in his head. So he probably did this whole, looks like Isaac, looks up here, and then there's the answer. Because to process, you have to do that. You can't process looking straight at somebody. Now, here's the other thing that would be interesting. What's the average of the numbers from 1 to 100? Well, I would have to add them all up, 5,050, and divide by how many numbers? 50.5, right? That's the average. The average of all the numbers from 1 to 100 is 50.5. That's how you do the averages. But what if I said I just took the first number and the last number, added them up, and divided by 2? I get the same answer. Why can I do that? Why is that possible? Here, let's do this. If I said find the average of those numbers, you could take the first number and the last number, 6, divided by 2, 3. And isn't that what the average of those numbers is? What if I squared the numbers? What if I did squares? You get 1, 4, 9, 16, 25. What's the average of those numbers? What's 1 plus 9? Say it. What's 4 plus 16?
20.
So this is 30 plus 25. It's 55 divided by 5. What's the answer?
11.
So the average of those 5 numbers is 11. What if I took the first number and the last number and divided by 2?
13.
They're not the same. Why not? What's different about these numbers than these numbers?
The top one runs in like a sequence, like a linear sequence, when the bottom one's exponential.
Linear versus exponential. When I have a linear sequence, what's the difference between those two numbers?
1.
What's the difference between those two numbers?
1.
No matter where I am in the entire sequence, the difference between the numbers is 1. What's the difference between those two numbers?
3. 9.
Okay, that's not the same difference, right? So that you can't do that. You can only take the beginning and the end and divide by 2 if it's linear. A linear sequence, you can do that. I mean, I could even take the numbers 2, 4, 6, 8, 10, right? What's the average? 10, 20, 30. 30 divided by 5 is 6, but I could take 2 and 10, which is 12, divided by 2, which is 6, because 2, 4, 6, 8, 10 is still a linear sequence. They're 2 apart. Okay, hold on. Let me do this. What if I said, I want you to graph almost erased the cliff, and then Sam would have been falling to the ground. Okay. If I graph these two things, what if I graphed velocity versus time? Which do you put on this axis? Which variable goes on this axis, the horizontal?
Time.
The time.
Because it's the independent variable. Do you agree that the velocity depends on the time? The time doesn't depend upon the velocity. At time equals 0, the velocity was 0. At time equals 1, the velocity is 10. At 2, 20, at 8, 80, are you getting the idea that this graph graphs up a line? Therefore, the average is going to be the midpoint of the line, where I could take the beginning and the end, divide by 2, and get this. This is a line. Okay, so this is a straight line. What do you know about a straight line? Is there something that's the same on the entire line? If you were on a bicycle anywhere on this hill and you started to go up, do you agree that starting would be the same difficulty no matter where I started? There's no place that's easier to get faster. So I want you to write this down, okay? Ready? The slope at any point on a straight line is equal to the slope between any 2 points which is equal to the slope of the line itself. Sam, are you still there? I think he fell asleep. Lena, what did you write down? Can you read me what you wrote?
Yeah, I have I'm sorry. The slope at any point on a straight line is equal to the slope between any 2 points, which is equal to the line itself.
Slope of the line itself.
Okay.
Now, I want you to think about this. What is the definition of slope?
The change in y over change in x.
Well,
Or y over x.
Boo. No, it's not. Do you see y and x on this graph?
Velocity and time.
Okay, so what is the definition of slope? That's always true. It's the rise over the run, isn't it? So this little triangle is saying that at this point, what is true about that point? That point is some velocity v. Remember this? We've done this before. What's this point on the line? Some velocity v. Are they the same v?
No, they're different.
If they're not the same, they're different. How different are they? The delta v. Do you agree that the rise is delta v? What's the run? This is some point on the graph, t. This is some point on the graph, t. Are they the same t? No. How? If they're not the same, they're different. How different are they? Delta t. They are different by the run, delta t. But what does delta v over delta t equal?
Acceleration.
Now, there's something we didn't do earlier and we should have done. What should we say about this acceleration? This, in yellow circle, is the average acceleration. And this one would be the what?
The instant.
The instantaneous, right? So make sure you spell that word, instantaneous. Acceleration is dv dt. So really, this is the average acceleration. The problem is, according to this, is the acceleration even changing? The acceleration is all the same. It's always 10 meters per second, which means this average is the same thing as every instantaneous point. The slope at any point is 10 meters per second. But watch this. Do you agree that this blue triangle, the slope is delta v over delta t? Okay, what about if I use this green triangle? Oops. What if I said this green triangle? Do you agree that it's still delta v over delta t? I want you to imagine that I'm making the triangle smaller and smaller and smaller and smaller and smaller. So instead of being 2 points, it's 1 point right there. That's the instantaneous acceleration, and the instantaneous acceleration can be written as dv dt. And we know the answer is 10 meters per second squared. Why? Because the acceleration is always 10 meters per second squared. So listen to this. The acceleration at any point in time is the instantaneous slope at that point. But the slope at any point is equal to the slope between any 2 points, which is equal to the slope of the line itself. And we know that the slope of this line is rise over run, which is a change in velocity over the change in time, which is 10 meters per second. They are not unrelated. And if I want to know the velocity, because the relationship of velocity versus time, do you agree this is linear? I can take the start and the final, any place I want, take the average, and it's going to be the right one. So what's my average? My average velocity from 0 to 1 second is 0 meters per second plus 10 meters per second divided by 2, which is what? 5 meters per second. which means during 1 second of time. I averaged this fast. How far did I fall? And the answer is 5 meters. Let me ask you this. Did you understand that? On a scale of 1 to 5, how well do you understand that that's 5 meters? If you want to go lower, Isaac, you can. Okay, so let me rephrase it. I'm saying that in that 1 second, because my velocity is increasing linearly, I can take the start and the stop, divide by 2 to find the average. I am falling at an average velocity of 5 meters per second for 1 second. The average velocity time to time gives me the distance traveled. I went 5 meters. Okay, so answer this question. If I go, how far do I fall from here to here? How far is this distance from 1 to 2 seconds? Think it out first. What do you think the answer is? Shannon, you got an answer?
Would it be 15
15 what?
meters per second?
No, how distance?
Oh,
15 meters.
Oh, that's the velocity. Yeah, sorry.
Right? Yeah, not right. So that's what I mean. You want to say that out loud. It's 15 meters. Do you guys agree that it's 15 meters? I mean, a lot of people are, their heads are going up and down. Lena, what did you say?
I totally could be wrong, but I did 20 minus 10, which is still 10, so that would be an average of 5 meters still.
No. Because to take the average, I need to take what so I'm only going from there to there. The duration of 1 second. What did I start with? In other words, what did I start here? 10. What did I end at?
Oh, so you add them?
So I add the two together. That's
Okay.
30 divided by 2
Which
is 15. So I averaged 15 meters per second
Okay.
in 1 second. Remember, the average times the time, V average times the time is going to be the distance that you fall. So 15 meters per second, right? 15 meters per second times 1 second. The seconds cancel, I'm left with 15 meters. Now, you could do that. How far can I go backwards? I did pretty good. What if I did this? What if I said, well, let's just forget about that. What if I said, I want to go from here to there? So I need the V average. What's my velocity average from 0 to 2?
10 meters
What did
per
I
second.
start with? 0. What did I end with? 20. What's the average? 0 to 10. 20. I mean 10 meters per second, right? For how long?
For 2 seconds.
10 meters per second for 2 seconds this time. And that means I've gone 20 meters. But isn't that, so the whole distance of 20 meters is 5 plus 15. Okay, so let's do this. How far do I fall in 8 seconds? Take the time and where's my is it recording? Well, what's the answer? Shannon, Julia, I mean, Shannon. I asked you last time. Julia?
I got 320 meters.
The rest of you get that? Right. Are you impressed? Are you impressed, Julia?
About what?
That you got the right answer?
A little bit, yeah. I thought I got it wrong because it seemed like a really high number, but
Well, right. So what I need to do is I started at 0. I ended at 80. Right? So what did I average in this time?
40.
I averaged 40 meters per second. For how long?
8 seconds.
That times 8 seconds is going to be 320 meters. That's it. Zach, have you taken physics before?
Once in high school.
Okay, so probably, and this keys me off here. You probably learned formulas. You learned the distance formula, and you use formulas. And then when you're learning formulas, you go, I need to put the numbers in the formula. And if the teacher gives you a problem where all the numbers fit, you're like, I can do this. And if they change a little bit of thing, you're like, I don't know how to do it because I don't know where to put the numbers. That's because you haven't learned anything. You're a monkey putting numbers in the calculator. When you learn to think, you can solve problems. And that's what education should be like. It's not, but it should be that way. But look at it. So Julia, does that make sense to you? You reasoned out what's going on. So what I want to see you do is really quickly, and I'm going to pause this. I want you to tell me, so remember, for time equals 0, you had delta, you haven't traveled anything. Or no, I'm sorry, not. When I say x equals, what does x equal mean? It means, what is x? X is the spot, right? So what I want you to think about is that I've got some graph over here that is the distance graph, right? Here's the distance graph. And on this graph, this is 0 meters, and this is 5 meters, and then 10, 15, 20. And so you see it all the way down, right? You're graphing it up. So at 1 second, x is what? 5 meters, right? At t equals 2 seconds, what's x equal? Where would you be on this line?
20 meters.
20 meters, right? And then we know that going all the way down, I'm going to erase all this for a second. It's out of my way. Going all the way down, I know that t equals, at 8 seconds, x is equal to 320, right? So I want you to take just a minute now and fill in 3, 4, 5, 6, 7. And I just want you to tell me that x equals all the way down. So can you fill that in? I'll just give you just a second to practice. Okay, so what would you get, Isaac? What's the next one?
For 3, I got 45.
45 meters. 4.
I got 80.
80. 5. What'd you get?
Would that be 125?
Okay. What'd you get for 6?
180.
And for 7 should be
245.
okay. So what I realize here is that when I look at the actual numbers, I'm getting this sequence. Anybody want to predict what the next number is without doing it, without calculating it?
It's should be like 9 times 45. So
Okay. Right. But I mean, looking at, what about if you just look at the pattern? How far apart is this?
5.
15, 25, 35, 45, 55, 65, 75. So this should be 85 more, which should be 405. Which 45 times 9 should be 405. So you could have seen that pattern. I want to see if you can see anything else about the pattern. Oops. Let's look at something else about the pattern. Anybody see anything else interesting about it? What number are all of these divided by, divisible by?
5.
Okay, what's 0 divided by 5?
0.
What's the next one?
1.
1,
4.
4.
9.
You seeing anything interesting? Aren't they all the squares? So it's 5. You divide each number by 5 and then multiply and then square it. So the next one would be 25. This would be 36. Whoop, 49. 7, 8.
64.
9, 81, 100. You just write squares. So what it is I'm really saying this. I'm saying delta x is going to be equal to 1/2 a times delta t squared, which is actually a formula that a lot of times in physics they'll give you. So why is it 1/2 of a? There's a reason for that. Oh, I want to erase that. That's a really big eraser, isn't it? Because I take the velocity initial plus the velocity final and I divide it by 2. But what's the velocity initial in all of these things? 0. So it's really the final velocity divided by 2. But the final velocity always comes about by the initial velocity plus 10 meters per second. The change is the final. That's where you get 10 divided by 2, which is 5. and then I'm squaring this. So that's where it kind of comes from. This is a square. But what I want you to do is, what if I graph this up? So I need to deal with this. By the way, this formula only works from rest. Or in other words, the initial velocity is 0. So this is not always true. This is only from rest. And I'll explain that to you later. So I don't want to leave that out there and think that's the way that you always answer it, because you'll be wrong. But I want to look at these numbers. Okay. Do you agree that these are exponential numbers? And I would like you to graph them up. I think that would be a great thing for you to do specifically, but I don't have that much time today. So I'm just going to go over here and I'm going to say, this is what the graph looks like. If I graphed time versus distance or the location, what I'm going to get is a graph that looks like this. Does that make sense? It's exponential. If I graph this up, I would graph, that would look like. That's what an exponential graph looks like. We've seen that in class before. Are we okay with doing this? Say yes or no. Okay. So what's the slope? Well, first of all, the slope at any point on a line is the slope of the line itself. But is this a line? Is this a straight line? This is a curved line. So I want to show you something kind of interesting here. The slope is still rise over run. Well, here, let me do it this way. It's still the rise over run. So do you agree that this is some value x? This is some value x. What is this? Are they the same x?
Nope.
So they're different, delta x. This is some value t. This is another value t. Are they the same t? If they're not the same t, they're different. That means this is delta t. The rise over run is delta x over delta t. But delta x over delta t is the average velocity. So that this graph is related to the average if I knew the average velocity. So what you could say is, well, I averaged 40 meters per second. This was 40 meters per second here. But what's the slope at this line? Make it smaller, right? Make it smaller. This over here, delta t, delta x, right? Smaller. What if I made it infinitely small? What do I get? I get a little triangle that's infinitely small. And what I end up getting, what's that line called?
Tangent.
I'm tangent. So write this down. The slope at any point on a curved line is equal to the slope of the tangent at that point.
Can you repeat that?
The slope at any point on a curved line is equal to the slope of the tangent at that point. What do you think? Does that make sense? Now let's do this for a second here. Let me undo as many of this as I can. Oh, crap, I didn't mean that. I want you to imagine this. What is the slope of this? Oh, sorry, that's bad. What is the slope of this graph doing as I go to the right?
Increasing at a greater rate.
Do you see that the slope is in, well, don't say that yet, Zach. Do you agree that the slope is getting steeper as I go to the right? Well, which way is the right? On this
Greater
graph, what is
time.
the right?
More time.
You wouldn't say that. Hey, I'll meet you at more time. What would you say? To the right on this graph is what? Lena?
To the right.
I mean, Zach said to the right is
Mhm.
greater time or more time. But you wouldn't say that. You don't say, hey, I'll meet you at more time.
Later.
Wouldn't you say to the right is later? Right? To the right is later. What's to the left?
Earlier.
Right? This is time equals 0. This is time equals 1, 2, 3, right? It's later. So what's the slope doing? It's getting greater as I go forward in time. But the slope at any point is dx dt. Isn't that the slope of the tangent? Didn't we say that over here? Look, up here, slope of a tangent, dx dt. So dx dt is your instantaneous velocity. So what's your velocity doing in this graph? Isn't it getting faster and faster as time goes on? Aren't I falling faster and faster as I give it more time? So I'm accelerating. Isn't that what I'm telling you I'm doing? I'm accelerating. The slope is the acceleration. And the slope of this line is increasing, and therefore, that's what an exponential curve does. Now, what I'd like you to do for next week, okay, so listen to me closely because I'm just going to say this once. I want you to redo this stuff, okay? I'm filling in T, V, A, and X. By the way, what is it? What's acceleration versus time? If I graph that out, what would that be? Isn't the acceleration constant, which is a straight line? What's velocity versus t? It's linear. What's x versus t?
Exponential.
Do you see how these things are all related to each other? Because I'm constantly accelerating, which means I'm going faster and faster and faster. But if I go faster and faster and faster, like Ryan said, I will go a greater distance in the same amount of time, which is an exponential speed. I mean, exponential distance traveled. So I'm going faster and faster and faster. I go further in the same amount of time. So what I want you to do is I want you to fill this in. T, X, or T, V, A, and X from 0 to 8 seconds. So I only did 1, 2, 3, and 8, or 1, 2, and 8. You do 3, 4, 5, like you did over here. The only difference that you're going to do is that Sam's going to throw me down at 2 meters per second. Calculate all those numbers. That's 1, or A. And then I want you to do it again. Same thing. But this time, instead of throwing me down, what if he throws me up at 3 meters per second? So in other words, what's the difference between down and up? Just a different direction. He throws me up. So what's my velocity is going to be what?
-3.
-3 meters per second. So fill all those in with those two numbers. So I should see all three of those listed out. You don't have to graph it up because you already know what the graphs look like, right? And then, any questions before I erase? The last thing I want you to think about, and this is what we'll talk about on next Tuesday, is this. I want you to walk this way.
Walk this way.
Okay, based on this graph, I want you to physically walk this. Okay, so you're going to do, here's what you have over the weekend. You're going to do, well, let me get you up here. You're going to do that assignment, fill in the chart. That's not going to take you long because you know how to do this. You should be able to do that. And then I want you to figure out, like, talk about it, talk to a parent or your one friend that you all have. Talk to your sister. How would you walk this way? Now, and you don't have to be right. I just want you to think about it. And then you have your outlines, all right? Your worksheets, I mean. That's all that's done. That's all you're going to have to do over the weekend. Today seems to be a pretty important lecture if you need to go through it and take better notes on it. But that's it. That's all I'm going to have you do. What'd you think? Was that kind of fun today? Dude, do you realize how geeky into physics you've just gotten? And next week we'll get into the winds because I lied. I said we were going to do winds today, but I lied. I forgot about gravity. Because that makes you understand why things are the way they are. But it's amazing what students in a right mind who are focused and attentive and thinking can do. Julia, I was so happy when you said 320 meters. Do you realize if you've ever been to an intro physics class, most people are like, what the hell's going on? They have no idea. And here you're like 320 meters. You're one of the geeks now. So you should all be proud of yourselves. I like all of you. I want to say I love all of you, but that might be weird, but I do in that weird professor type way. Aaron, if you're looking, if you're watching, where did you guys all go? Oh, here, I need to do this. That's what I need to do. Aaron, I know you're watching this. We miss you. Hope everything's good. And the rest of you guys have a great weekend.
Thank
too.
you.
Thank you.
See you on.
Have a good weekend.
Bye.